Hello everyone, welcome to the Better Science channel. I'm Cao Jing and I'm the application engineer at Better Science Instruments. Today I'm going to share an easy and high-efficient method of measuring the isoelectric point of materials. Before sharing this method, I will talk about two simple concepts first: zeta potential as a function of pH and the isoelectric point. If you are already familiar with these concepts, you can skip this part and directly get into the second part. In the second part, I will share the method and introduce its features and benefits to you. In the last part of this video, I'm going to share some practical application cases with you. If you are interested, please continue to watch. You must have known the zeta potential is the electrostatic potential at the shear plane of the particles in a colloidal system. It can be influenced by the surface charge of the particles, the activity of a hydrogen ion in an aqueous solution. In other words, the pH of the environment can influence the surface charge of particles by controlling surface ionization. For example, the amino group is protonated and becomes positively charged in an acid solution within a low pH range, but carries no charge when the pH becomes high enough. The carboxyl group is negatively charged in a base solution within a high pH range, but carries no charge when the pH becomes low enough. Generally, when in an aqueous system with lower ionic strength, the particles that carry positive surface charges at a low pH have a positive zeta potential. The particles that carry negative surface charges at a high pH have a negative zeta potential. And the higher the degree of ionization, the higher the density of the surface charges, the more adsorbed ions surround the particle, the thicker the electric double layer, and the greater the absolute value of zeta potential. The isoelectric point is the pH at which particles carry no net electrical charge and have the thinnest electric double layers. The zeta potential is close to 0 mV. When the pH is lower than the IEP, the zeta potential is positive. When the pH is higher than the IEP, the zeta potential becomes negative. And with the pH far away from the IEP, the absolute value of the zeta potential becomes greater. The zeta potentials of homogeneous particles generally have the same sign. Thus, it shows the electrostatic repulsive force between each other. So, the IEP indicates the weakest electrostatic repulsive forces between particles. At IEP, particles are prone to agglomerate, and the stability of the system is the worst. So, what method and instrument can help us obtain this useful parameter? The answer is the electrophoretic light scattering technique plus multi-step pH titration. ELS is a light scattering technique that measures the zeta potential of particles suspended in solution. The binano nanoparticle analyzer is the instrument that uses this technique. The BAT1 autotitrator is an accessory for the binano that is used to perform multi-step titration. It can automatically titrate the sample from any pH to the target pH by a set step size. The BAT1 autotitrator consists of a pH probe, a sample container, 3 titrant containers, a built-in magnetic stir, and the inside pipelines. The titrant cabin can be put out like a jar for ease of operation. This is the schematic diagram of the pipeline. During titration, the stepping motor drives the transmission mechanism and syringe pumps to deliver the titrant into the sample container. When using titrant 1, valve 1 is open to allow titrant 1 to pass through. Meanwhile, the other 2 valves are closed. Each titrant has an individual delivery pipeline for avoiding cross-contamination. During titration, the pH probe measures the pH in real time. Once the pH reaches the target value, the sample pump will work to circulate the sample into the binano to measure the zeta potential. All these steps, titration, delivery, and zeta potential measurements, are controlled by the binano software via an SOP. Now, let's make a comparison between manual titration and automatic titration about how many are required steps of measuring Z potential as a function of pH. When we do it manually, measuring one sample maybe need dozens of steps and take an operator a whole day. It's time-consuming work and needs a lot of patience. When using the BAT1 auto-titrator alongside Binano, getting all the results only needs 5 steps. You just need to prepare the titrants in the titrant containers, calibrate the pH probe by the software, create an SOP, start the test, and then you can do something else. Let the machine run by itself. When the test is completed, check the results in the software. All preparation and maintenance operations only take an operator around 15 minutes. It's very convenient and time-saving. The required input parameters in the SOP are refractive index and viscosity of the medium, concentration of the titrants, and the initial volume of the sample. And after the test, you will get Z potential as a function of pH, the IEP, and conductivity. These results can help researchers study the surface charging behaviors of materials over a range of pH conditions, analyze the material stability, characterize the chemical interaction capacity of the materials. It provides researchers with a direction for improving their products. And the automatic system can make measurements simpler, more efficient, more accurate, and safer, obtaining more measurement points within a shorter time, better consistency and repeatability of the results, reducing the workload of researchers, lower requirements for operators, reducing exposure to corrosive liquids, keeping lab clean and tidy. Now, let me introduce 3 main features of the multi-step titration system. Feature 1. The high-precision pH adjustment. In the titration sequence interface, users can customize titration conditions containing titration range of pH, the titration step, how many pH points to titrate, and the pH tolerance of the targets. During titration, the system monitors the pH in real time to ensure the price control of titration, and the system can select the optimal titrant and adjust the addition volume intelligently to optimize titrating efficiency and accuracy. So operators can prepare 2 or 3 acid or base titrants with different concentrations to provide options for the system. The syringes with low volume displacement and well-characterized plunger diameters allow the accurate addition of small amounts of titrants, as low as 0.28 microliter, which enables price targeting of the desired pH. Feature 2. Easy maintenance. The maintenance of the BAT1 auto-titrator is very convenient. It only takes around 2 minutes to calibrate the pH probe with 3 clicks. In the non-test state, the BAT1 still can be controlled manually by the software to empty and clean the pipeline. The cleaning work won't take more than 5 minutes. Operators don't need to wash a bunch of beakers. The operation becomes very simple. Feature 3. The user-friendly software. One-click installation, intuitive interfaces, and easy to navigate are part of the features of the Binano software. It doesn't need strict training in how to use the software or take a long time to get used to it. Here is a summary of the benefits of BAT1 auto-titrator versus manual titration. Up next, I will introduce some applications and share with you some measurement cases with the Binano and the BAT1. The Z potential versus pH measurement is widely used in many fields, including ceramics, fillers, vaccines, pens and inks, water treatment, and polishing fluid. Here are the IEPs of some materials cited from Big Chemical Encyclopedia. We can see that the same material has very different IEPs due to their unique crystal forms. And the IEP of a material is not constant. It may change with the variation of the surface groups coming from surface modification. Here is a case for measuring titanium dioxide with Binano and BAT1 auto-titrator. The sample was titanium dioxide aqueous system. and the titrant is hydrochloric acid. The titration range was set from the current pH to 3, and the pH step size was set to 1. The tolerance was set to 0.2. When the test was complete, we got the Z potential curve like this. It contains 8 pH points. We can see the original pH of the dispersion is around 9.6, and the Z potential is around minus 25 mV. With the decrease in pH, it reaches the IEP at pH 7.5, and with the further decrease in pH, the Z potential becomes positive, and the absolute value becomes greater. So this titanium dioxide dispersion has the worst stability when the pH is close to 7.5. If the user hopes to keep this powder dispersing stable in the system, the pH of the system has to be just far away from 7.5. The conductivity plot shows that the conductivity of the dispersion becomes higher with the decrease of the pH, due to the ionic strength becoming stronger with the addition of acid. The second case is the measurement of aluminum. The sample was aluminum aqueous suspension. The titrant was also hydrochloric acid solution. The titration range was set from the current pH to 2. The pH step size was set to 1, and the tolerance was 0.2. From the resulting curve, we can see that the IEP of this suspension is around 7.9. However, even if the pH is much higher or lower than the IEP, the Z potential is still low, not high enough to keep dispersing stable. So if the user hopes to keep the particles separating stably, it may be not a useful way to adjust the pH of the system. The third case is the measurement of proteins. We prepared the sample by dissolving the BSA in a sodium chloride solution. The titrant was the hydrochloric acid solution. The titration range was from the current pH of around 7 to pH 1. The step size was 0.5, and the tolerance was 0.2. Finally, we got the Z potential of BSA as a function of pH. The IEP is around 4.1, so this BSA sample won't be very stable in acidic environments. That's all for this video. I hope it's useful to you. Thank you for watching. Bye.